Hello there, Mr. Sutton here, bringing you this lesson on independent and dependent events. In this one, we are going to find probabilities of these two different types of events. And for the real-life app, we're going to determine the probability of drawing 3 hearts from a deck of cards, both with and without replacing the cards as we go. For the warm-up on this one, this is more of a pause and ponder kind of warm-up. Let's say you draw a card from a standard deck. Without replacing the card, you draw another card. Do you have the same chance of drawing a king both times? Why or why not? So what we're really getting at with this one is, the first time you draw the king, it is what it is. There's 4 kings out of 52 cards. Those are your chances. Do you have the same chances the second time around? This is getting us into our topic today of independent versus dependent probability, where one event can affect another event. The first type of events we'll talk about are independent events. These are events that do not affect each other, which is to say we're not changing the favorable or possible outcomes for one event by doing the other event. So, for example, rolling a die and flipping a coin are independent. Regardless of what I roll on this die, I'm still going to have 2 sides that I can get by flipping this coin. So to find the probability of whatever outcomes we want from both of these happening, the probability of independent events both occurring, it's going to be the product of their individual probabilities. So you find the probability, for example, of rolling a 6 and the probability of rolling a head, and we're just going to multiply those probabilities together. So if you're looking for a formula, we could say P of A and B equals probability of A times probability of B. And just one more little notational thing, P of A and B can also be written as probability of A comma B. These mean the same thing. Let's go ahead and take independent probability for a test drive. Let's say we have a spinner for some board game, and we want to find the probability that we get a 5 on the first spin, followed by a number greater than 3 on the second spin. What is that probability going to be? So first thing we should do is verify whether or not these events are actually independent of each other. Does spinning a 5 the first time around affect what I can spin the second time around? It doesn't. This game board's not going to change in any way after that first spin. So because our spin results are not going to affect each other, we say these events are independent, which means we're just going to go ahead and do what we said on the last page, find and multiply those individual probabilities. Pause the video and see if you can do that. All right, so the probabilities, we've got the probability of spinning a 5. That's a 1 in 8 chance, since these are all equal areas, they said in the beginning of the problem here. So 1 out of 8. And now we want the probability of a number that's greater than 3. Well, how many numbers are bigger than 3? That's going to be 4, 5, 6, 7, and 8. So 5 numbers out of 8. That's going to be a 5/8 chance. So the probability of both of these happening, since they're independent, is just going to be 1/8 times 5/8. And let's see here. That's going to be 5 over 64, which I can't reduce. So that's my final probability. So I think we can agree on that last example. We kind of dodged a bullet with the fact that the events were independent because we don't know about dependent events yet. But now we're going to talk about this. Dependent events are events that do affect each other. So for example, drawing 2 cards from the same deck without replacement, because you can't draw the same card twice. So if I draw the Jack of Spades on the first round, that affects my chances of drawing that same Jack again. Namely, my chances are now 0. Now, how do we deal with events that are dependent? I think we can agree that the first event of the 2 is just going to be normal probability because nothing has changed when the problem starts. But after that first event happens, that second event's probability is going to be kind of special. We have a special name for it. We call it conditional probability. The conditional probability of event B given A, which we can symbolize with this little P of B with a line and then A. This little line means given. This is the probability that your event B occurs given that event A has already happened. So this is, for example, you could say the probability of drawing a Jack given that one Jack has already been drawn, and now we know that we have to factor in that earlier event. It also gets used in other ways. For example, if I have 6 cards numbered 1 through 6, normally the probability of drawing a 3 is just 1 out of 6. But now let's say I only choose from the odd cards. We could frame this as a conditional probability kind of situation, we can say the probability of drawing a 3 given that I'm only picking from the odd cards. And now the person looking at this knows, okay, I'm only looking at the odd cards. Now I have a 1 in 3 chance instead of a 1 in 6 chance because I'm no longer looking at the original sample space. So conditional probability, we're using it in the context of dependent events, but it's really its own animal, and we're going to have 2 extra lessons on it down the line. But back to the original context, if I want to find the probability of dependent events, that's going to be the probability of the first event, just normal probability, times the conditional probability of the second, given that the first has already happened. So if you're looking for a formula for this one with dependent events, we can say probability of A and B is going to equal the probability of A times the probability of B given that A has already happened. Let's take a look at another example now to hopefully clear up any questions you might have on this whole dependent event idea. So we have a bag with $21 bills and $500 bills. Nice. We randomly draw a bill from this bag, set it aside, and then randomly draw another bill from the bag. Find the probability that the first bill is $100 and the second bill is $100. Well, the key here is that we're setting the first bill aside and not putting it back in the bag. So that means that whatever we draw on that first event is going to affect what we can draw on that second event. So because the first draw affects the second, we would say that these are now dependent events. If we put the bill back, they would be independent because it would just be starting over, basically. But when we change the number of bills in the bag, that makes this a dependent event. So to get the probability of both of these happening, we need the probability of drawing that first $100 bill, which since we have 25 overall and 5 of them are $100 bills, that's just going to be 5 out of 25, or 1/5. But now this second event is not quite the same. This is a conditional probability. This is the probability of getting a second $100 bill given that we've already drawn that first $100 bill. So things are going to change because we have one less $100 bill because we already drew one the first time, and we also have one less bill in general. In general, these conditional probabilities, you're always going to be messing with your total number of possibilities, but in this case, it looks like we're also messing with the favorable outcomes. So pause the video and see if you can figure out what the conditional probability should be. All right, so we have 24 bills instead of 25, and now we have 4 $100 bills instead of 5. So this is now 4 24ths instead of 5 25ths. And we can reduce that to 1/6. So clearly, these are not the same probability. The good news is that we're still just going to multiply them together. So this is going to be 1/5 times 1/6. The only difference is that we have to work a little harder for the second probability. So overall, then, we have a 1 out of 30 chance of making this happen. Now, in general, just a tip here, it's a good idea to reduce as soon as you can, just because you are going to be multiplying fractions together. So this makes it so you don't have to reduce as much later on. So we've seen independent and dependent probability. All right, it's time to see if you can pick out which is which. So we're randomly selecting 3 cards from a standard deck of 52. We want to know the probability all 3 cards are hearts when, so 2 different conditions here. Version A, you replace each card before selecting the next card. Version B, you do not replace each card before selecting the next card. So find both of these probabilities and then go ahead and compare them, probably by just finding the decimal for the probability. All right, let's see how you did with part A. So if we're replacing each card before selecting the next card, we're basically starting over with our sample space each time. So these are going to be independent events if you replace each card, because nothing changes in terms of what your possibilities are if you start with the same deck each time you draw something. So the probability of drawing 1 heart. There are 4 suits, and hearts are one of those 4, so you have a 1 in 4 chance. Or you could say, oh, there's 13 hearts out of 52, and reduce it to 1/4. Now, we want this to happen 3 times in a row. Each time we do this, though, we're replacing the card, so it's still going to be a 1/4 chance each time. So we have 1/4 times 1/4 times 1/4. This is the probability of drawing 3 hearts in a row. Multiplying these together, we've got 1 over 64. Which, let me just plug that in the calculator. Plugging that in, that's going to come out to, let's see, about 1.6% and some change. All right, let's try the other way now. Let's go back now and do part B of this example where we do not replace each card, so no replacement this time around. Independent or dependent? Well, since we're not replacing the cards, that means each time we pick, we have one fewer card to choose from than we did last time. So for that reason, these are going to be dependent events if you have fewer cards each time. You might also have potentially fewer hearts that you're able to pick each time. So in many ways, dependent events. Given that, let's go through now and find the probability of doing this 3 times in a row. The first time around, before anything has changed, we still have a 1 in 4 chance of picking that first heart. After we pick that, though, we now have 1 less heart and 1 less overall card in the deck. So whereas before we had 52 cards, now we have 51. So we have a total possibilities of 51. And for the numerator, well, before you had a 13 out of 52 chance, now there's only 12 hearts. So 12 out of 51 is the probability of the conditional probability of picking that second heart, given that you already took a heart away. How about the third heart? Well, if we take another heart away, now this is down to 11 out of 50. So the probability of the third heart, given that you've already gotten the first 2 hearts, 11 out of 50. Now to get the probability of all of these happening, we're going to multiply them together. So 1/4 times 12 51sts times 11 50ths. And I'm going to use the calculator to figure this one out as a percentage. So for the numerators, I've got 12 times 11. That's 132. For the denominators, we have 4 times 51 times 50. That's 10,200. So there's kind of the original fraction. Now dividing these, I've got 132 over 10,200 for a percentage of about 1.3% if we round off. Now, you'll remember that our percentage the last time around, or you can sneak a look back here, but it was 1.6% when we replaced the cards before picking again. If we don't replace the cards, that's down to 1.3%. So without replacement, we have a lower chance of getting our 3 hearts. And I guess we could keep going, but I just don't have the heart for it. So we're going to stop here. Until next time, this is Mr. Sutton signing off.